So exercise 96. So let me don't say recall, let me put remark. There are wireless functors between Galois representations and semi-linear algebra categories. We are different kind of rings to construct the functors. Those rings equipped with some structure Frobenius, filtration, Galois action, etc. We wish to extremize this kind of situation. For constructing and analyzing functors defined by some so-called period rings. In order that we don't have to repeat similar arguments every time we introduce period ring. So this part I'm following the lecture notes, so Brinconar and Olivier Brino the CMI notes. So second remark, this is part of definition. Let F be a field and J a group. Let B an F algebra. Domain, required to be a domain also, equipped with G action. So as an F algebra, which means this G action is compatible with the F algebra structure. And assume the invariant F subalgebra It's denoted by E, fixed point under G inside B. We assume this is a field. We do not impose any topological structure. On B or F or G, not yet. Our goal is to use B to construct an interesting factor. From finite dimensional F-linear representations of G to finite dimensional E vector spaces. And this will be endowed with extra structures. So depending on what structure we put on B, So this B will later be period rings, right? So we'll exorcise this construction. So by choosing a nice B and then construct a functor which from the category of representations of G to some semi-linear object, semi-linear category. So the notation, we denote C to be a fraction field of B. This is a domain. And then G acting on elements of C just by G will be 1, and then B is F algebra, and then G will be 2 just. Okay, and then force remark definition. We see that this B is F G regular. If fixed point of C under G equals fixed point of B under G, and if every non-zero element of B such whose F linear span is G stable, implies that it is a unit in B. Okay, I hope this is written clearly, which means B is non-zero plus FB is J stable, implies B is unit. .1, notice that if B is a field, then the condition in the definition for above is always true. Because it's non-zero, if it's G stable, then it's non-zero element. Then I mean, if it's not zero, it's already, because this is a field, it's already in a unit. Okay, nothing to check here. Now let's show that Tate-Sen theorem, I'm going to state it, implies, gives us two examples. I'm going to mention it here. So first, let's recall what is this Tate-Sen theorem. Let me just write it down, put it here. So recall this Tate-Sen theorem. For any p-adic field K, we have fixed point of CK under GK is K. So CK is the valuation algebra closure and then valuation completion for the field. And which means that, so because the CK is a transcendental extension of K, because it's p-adic completion of the algebra closure. But when you take the GK invariant, you notice that it comes back to K, which means this is the same as K bar of GK. This is just telling you that there are no transcendental element that are fixed by J. There are no transcendental invariants. And the twist of this CK, we fix it by GK, it becomes 0 for R non-zero. In other words, if small x is in CK and the collection is by the Tate twist, for all J in JK, then this x must be 0. Also, this theorem tells us that the first cohomology group of GK, so the GK module is CK twisted by R is 0. If this R is not 0 and this first continuous cohomology of JK for CK is one-dimensional over K. Recall that, so we have done exercise before, so this H1 continuous, it classifies all semi-linear continuous scalar representation. When you put GLN of some field B there, right? But so here's not exactly the same thing, but just mention that. Of course, you could think of this as GL1 of B, right? Take this B to be the CKR or CK. This tell you that this is one-dimensional continuous semi-linear action from JK to CKR representation. This is telling that there are only trivial CKR semi-linear continuous representations. Okay, there is only trivial one and canonical one-dimensional CK representation, continuous and semi-linear, right? More generally, this is still part of the theorem. To put this condition more generally, if eta is not necessarily the cyclotomic, but is a continuous character such that eta of JK is a commutative p-adic. Lie group. Dimension at most one. In other words, eta of JK is finite, or it contains ZP as an open subgroup. Yeah, this part needs to be understood in a more detailed way. Anyway, we will not use subgroup structure for our purpose later. And if this color representation is CK eta, which means it is CK as module with this scalar action coming from a kind of twist by eta. Then the conclusion is that the continuous group HI, JK, CK of eta equals 0 for I equals 0 or 1 when eta ik is infinite. And these cohomologies are one dimension over K. When this image is finite, so this IK is the inertial group of GK. In other words, when the splitting field of eta over K is finitely ramified. Then again, this need to be explained in details, but this is what we need. So in particular, so this is really a more general situation. So let's say the two examples comes. Yeah, we're talking about examples of FG regular domains. So first example, let K be a p-adic field with a fixed algebra closure K-bar and let CK denote the completion K-bar. And we let J equals JK to be the Gala group, and B equals BHT Hashtag, and 0 to be the Tate twist of CK, and the direct sum. So this gives you both structure as Galois audio and as a CK module. That with its natural J action. So non-canonically, this ring could be regarded as polynomial ring over CK and over T, so this T corresponds to, which gives us the twist, the small t. And so when you apply Galois group element on, let's take an element inside this B in the form power series, this is defined to be. So firstly, acting on the coefficients and cyclotomic vector, and then on the T power. So in this case, C is defined, we call it to be frank of B. This will be just Ck of T. And we claim that this B is Q, P, and J regular with this E point fixed of G under points of B fixed under G. This is, in this case, K itself. So the transcendental element is not fixed. Ck fixed point is K. You can think of this as part of a result from the Tate-Sen theorem. Now by the Tate-Sen theorem, this fixed point of B under G have decomposition. So this decomposition comes from the fact that we have already described here. Okay, the Tate-Sen just tell you that when we take the fixed point, this is just their sum of K when n equals. This is just either K or 0, depends on what is the R. If R equals 0, then this is K. If R is non-zero, then this is 0, and so this is just finally just K. This is a more detailed explanation. Okay. Now let's put at the exercise, why not? So exercise 1, show that CG, so C is frank of B, also equals K. So let's consider this C included in the formal power series ring, which is also GK equivalent. So it suffices to show the latter point fixed is K. And then let's recall, so this Galois action on this formal power series, this is again given just by So this fixed by G condition is equivalent to telling you that this GCN must equal CN. For any n z. In other words, the Cn is in this CK fixed by J, which is K. Sorry, yeah. This is equivalent to telling you that Cn is inside Ck twisted by N fixed by Jk for any n in Z. And then by our arguments here, Tate-Sen argument, this is telling that C n equals 0 and different from 0, and C0 is contained in Ck, Jk, which is K. And so this is equivalent to telling conclusion. So this Jk equals K for, so only the degree 0 term could be non-zero, and it must be K, elements of K, and all those degree non-zero term must be 0. So now exercise 2, verify this B. Recall its definition is, could we think of this? So more rigorously it is Hochstadt. Verify this is, we have already verified first term. Second term, verify this is FG regular. As we claimed, this is QPJ regular. What is only left is the second condition, right? It's left to show if B is non-zero, and then what is F here? F is QP. This is GK stable, this line, then B is in the unit of B, right? So let's check it. If we have small b spans a JK stable QP line, then JKX on the line QPB by some checker. This is stable, GK stable, so it cannot be 0, right? And so from JK to QP star. It is a crucial fact follows from the continuity of the JK action on each direct surround of B. That C must be continuous. And so it takes values in ZP star. Put this as some exercise to think about it. Now we're writing log polynomial small b as the form Cj times t to the power j. Then we have C j acting on B equals j acting on B equals, by definition, chi j to the power j tj and then jci. So this is the condition that this is JK stable. This chi through the chapter C, so the G action on it is the same as the JK action on this B, because this small element, small b, is taken from B, right? Notice this small b is taken from this B, HT. this condition is just saying that while your J action stabilize this straight line, so this is again in this straight line of QP of B, while this is the Galois action in view of an element in this BHT. I mean, this chapter is just because it's stable, it's JK stable. So which means, how is this defined? So say of J is actually defined to be so J acting on B equals C of J on B, and this C of G exists because this is claimed to be JK stable. And so if you look at for each J, say inverse composed chi, J acting on J. So this is QP, then times J of Ci. So this is Ci is element of Ck. So this is in Ck equals Cj. In other words, we have C of J times each Ci equals this, and we translate back exactly to this for all J in Jk. That is each Cj is Jk invariant through the chapter C minus 1 composed chi of J. Again, by the Tate-Sen theorem, for Vp star valued continuous chapter eta of Gk if this Ck eta has non-zero Gk invariant. invariant element. Then checker restrict on this inertial subgroup has finite order. Hence, as each say j is inside this GK invariant, and of this checker, so this restrict to IK, has finite order if those Cj are non-zero. So each Cj corresponds to this chi j. It follows that we cannot have two Cj and Cj prime not zero for different j prime, because otherwise this would give us x chi j minus j prime, and this j minus j prime restricted to the inertial k has finite order, because each of it has finite order, and so the quotient has finite order. And this would imply this chi has finite order. But this is a contradiction, because this cyclotomic checker cuts out an infinitely ramified extension of K. As a result, there is at most one j that it has Cj non-zero. And there must be such one, because this b is not zero, hence b equal to some c times tj for some j. And some c non-zero in K. This implies actually b is unit element in B star.